Hi everyone, this is Mahesh. In this video we will see introduction to time complexity. So in few of the earlier videos we understood how important it is to select a right algorithm and also a right data structure to have a proper efficiency. So we always talk about efficiency when it comes to algorithms or data structures. Then how do we measure this efficiency? Is it something that we write the algorithm and then give it to a computer and wait for its execution time and see which one is efficient? Is that the case? No, I don't think that is the case here. So since whenever we write an algorithm, we write the raw algorithm, so it is better to understand the complexity in the raw way. So if that is the case, then how do we compute this time complexity? So before that, let us try to understand growth functions. So what are growth functions? Growth functions. What are growth functions? They are also called polynomial functions mathematically. So let us take a small graph and try to understand. So this is the input axis and this is the output axis. So now as the input increases, the output also increases. So if we look into this graph here, so as the input keeps on growing, the output is also growing. So this is what is normally called a growth function. So if we keep on increasing the input size, then the output will increase. Let us take a small example. Say for example, function f of n equal to 2n plus 1 is an example. So here, if n is equal to 10, then it will be 2 into 10 plus 1. This is 20 plus 1. Now let us take n equal to maybe 100. This will be 2 into 100 plus 1. This is 200 plus 1. Let us take larger value of n. Say for example, let n is equal to 10,000. Then in that case it is 2 into 10,000 plus 1. So now if you see, this term is constant and it is not I mean it never increases. But if you take this n value, so if n value increases, the output of this function will also increase. So one thing what we can observe here, so this constant term is not contributing much here, but this value is contributing more as and when the value of n keeps on increasing. So what we can write, somewhere f of n is somewhere close to 2n. Yes, but this is also a constant term. There is no much impact on from this term as and when the n grows. So we can somewhere say f of n is equivalent to n. Yes. So now if this is the case, then we normally represent it as big O of n, which is order of n. So here the output grows in linear term, or as the n increases, the output increases. So this is one example. Let us try to consider one more example. Let us say f of n is equal to 2n square 3n plus 10. Okay, let us take smaller values of n. So n equal to maybe 10. So this will be 2 into 10 square plus 3 into 10 plus 10. Now this will be 200 plus 30 plus 10. Now let us increase the value of n to maybe 1000. So this is 2 into 1000 square plus 3 into 1000 plus 10. So this will be larger, plus 3000 plus 10. Let us take still more larger value, which is maybe 10 raised to 6. So this becomes 2 into 10 raised to 6 plus 3 into 10 raised to 6 plus 10. So if we consider this particular term, here we know from the earlier equation this is a constant, its contribution to the output will be very, it's a constant term basically, and 3n and 2n square are going to contribute to this particular f of n. So there is a purpose why I am trying to explain this. Okay, so now as we increase the value, this term becomes very big and this term is also a little bit big comparatively. This is constant. So now what we can say, this is somewhere equal to 2n square plus 3n. Okay, but if you see, as the value grows bigger and bigger, this is also kind of negligible. Its contribution will be more because it is increasing in terms of square. So somewhere we can say f of n is close to 2n square. Since it is a constant, we can also say it is somewhere equal to n square. So we can write it is of order n square. It is of order n square. So basically it is a polynomial function in mathematical terms, and we consider the highest degree of the polynomial function, and this is the big O representation or asymptotic representation of this particular polynomial equation. So this function which is 2n square plus 3n plus 10. So if we consider larger values of n, then the contribution of the highest order term is more, and that term we consider to compute the asymptotic equation of this particular polynomial. So basically this entire term is somewhere represented in terms of order n square. Okay, so this is how we normally try to represent the contribution of a particular polynomial function in terms of big O notation. Now let us try to correlate this with the program. Okay, so let us take a small function. So this is a function which takes a and b as input and it returns a plus b. So basically what it does, it will take inputs a and b. And how do we consider the computation time here? So since this is one particular action that is happening, we will take it as 1 unit of time. We will take it as 1 unit of time. So whatever be the input here, so you give 10, 20 or 20, 30, whatever the inputs you give, what it does, it will take 1 unit of time and it will return us the output. So if that is the case, then what is the time complexity of this particular equation? It is of order 1 or it is of order some constant, because this is a 1 unit of time, it's a constant unit of time for this particular function. So this is a simple function. So what I was trying to say, one execution, we consider it as 1 unit of time in this function. Okay, so now let us see a small for loop. We have a for loop which starts at 0 and I less than n, I plus plus, and then it prints something. So it prints something. So we already know this print function, this print will take 1 unit of time, normally 1 unit of time. If this executes only one time, then it will be 1 unit of time. But this one, this will execute n plus 1 times. How n plus 1 times? It starts when I is 0, it stops when I is less than n. So if you take n as an, say for example, n is equal to 10, then it stops, the increment of I stops when it becomes 10. So it means it started at 0 and it ended at 10. So which means it will be 11 times. It executes 11 times, which is n plus 1 times. So if it is executing n plus 1 times, but it stops at n plus 1 time, the inside thing will execute only for n time. So this will execute for n times. So if we add up, it comes somewhere to n plus 1 time. So if this is the function, if this is the growth function of this particular for loop, then we already know how this can be represented in big O notation. We will only consider the highest order term in this polynomial function, and we will write it as big O of n. So big O of n is the time complexity of this particular function. Okay, let us take one more example. Now let us take a little bit complicated one. Till now we had only one for loop, and now we will assume there are two for loops. So j equal to 0, j less than n, j plus plus. Okay, so now we are going to print something here. Now how to compute the time complexity for this one, or the execution time for this one? Let us say this executes for n plus 1 times, this executes for n plus 1 into n times, because this executes for n plus 1 times, but inside of it executes for only n times. So this executes for n plus 1 time, and because of this outer loop we are multiplying it with n. So this becomes somewhere n square plus n. Now this executes n into n times, so which is n into n, which is equal to n square. So if we sum it up, it becomes 2n square plus 2n plus 1. So if this is the growth function or the polynomial equation for this particular for loop, then what will be its time complexity? We have already seen. We will take the highest degree available in this particular polynomial function, and we will write it as big O of n square. So it is of order n square. So these two for loops will take big O of n square time. So this is how we normally compute the time complexity for the loops or any algorithm, because normally algorithms will run these loops and all. So further we will see how to come up with this time complexity for different polynomial functions, and we will see some more examples in the upcoming video. Thanks for watching this video.